As you can tell, I very much am an astronomer and not so much a physicist. So the things I'm going to be talking about are going to be taking a very astronomical take on the problem of exoplanet system age inferences. And so if you know something about planet formation and evolution, and even if you don't, I'll be telling you, that there's a lot we could learn if we had better age constraints on the host stars of the exoplanet systems, with of course thinking that the system and the host star are the same age, that would tell us things we don't already know about how those systems form and how they live their lives over the billions of years of their existence. So the work I'm going to tell you about is primarily the PhD work of JHU graduate student Jacob Hamer, who is a Hunter College alumnus. And this work is supported by the National Science Foundation. So the first slide in every exoplanet talk looks something like this. This is the distribution of known exoplanets on a log-log scale with orbital period on the x-axis and mass on the y-axis. The green points are individual planetary systems that have been discovered, and the blue points are the planets in our own solar system. So this diagram tells us there is structure. There are planets like Jupiter, maybe there's a little bit of a gap. There are planets very close to their host star, although of course this is because of observational biases. In a second, I'll show you a slide that does a much better job showing what's going on. There are smaller, lower mass close-in planets, but maybe not so many things that we've yet discovered like Venus or Earth. Now, if you want to look at a less biased view of this, this diagram actually encodes the occurrence of planets as a function of orbital period and mass, and not just the number of planets that we know about, which of course is heavily biased. This is the same thing, orbital period on a log scale on the x-axis, mass on a log scale on the y-axis. The darkness of the blue, the opacity of the blue in this diagram encodes how frequent planets are in that sector of orbital period and mass. So there are many more low mass planets than there are high mass planets. And there are more long period, or at least out to about the orbit of Jupiter planets, than there are short period planets. And so if you want to understand what the most common outcome of planet formation is in the galaxy, one would need to study both the longest period, or at least maybe out to 5 or 10 AU, and the lowest mass planets, because that's what most commonly is produced. So now I'm going to violate my advice and not talk about those, and in fact talk about the close-in, heavily biased ones, because that's where the physics of tidal evolution starts to play a role. And in fact, this is tied into what is literally the second, as of yet, or at least before Jacob entered the scene, unknown problem in exoplanet astrophysics. This is a different view of this same thing, which has been enabled by transit surveys. So the very first diagram I showed you on the y-axis had the mass of the planetary system. That's something that we can infer based upon Doppler measurements. If the planet transits, then we can also infer the radius of the planet. Of course, if you have both the radius and the mass, that tells you something about the density, that tells you something about the structure of the planet. So this is orbital period on a log scale on the x-axis, and now radius on a linear scale on the y-axis. And this backs up what I said earlier. There are many, many more small planets than there are big planets, even though the observational selection effects are such that the big planets are much easier to see. Anyway, so these two diagrams are what people typically show when they talk about using exoplanets, the exoplanet population, and then doing some statistics on it to figure out what might be going on. But of course, this is only 3 dimensions that I've shown you. And there are several other dimensions that one could give entire colloquia talks about. So the first maybe is stellar multiplicity. What effect does a binary or a tertiary companion have on the planetary system that results? There's been a lot of excellent work on that, perhaps suggesting that maybe close-in planets are okay, but maybe longer period planets are less common in stellar binary systems. Host star mass. So we have now a range of about 20 times in host star mass, from maybe 2 solar masses all the way down to about 0.1 solar masses, where we've seen different planetary systems. That clearly has some role to play. The metallicity of the star, which we think encodes the composition of the protoplanetary disk. This is something that was one of the earliest clues we had about the formation of giant planets. That is a very strong connection between the occurrence of giant planets and the metallicity of their host star, which we understood to be that it's easier to make giant planets in disks where there's lots of planet-making material. Host star evolutionary state. So Sam Grumblatt, who is a member of the CCA community, he's working a lot on this question right now, trying to find planets around evolved stars and maybe see how those planetary systems differ from the planetary systems that have been studied around main sequence solar type stars. Planetary systems can also change because of changing galactic environments. So it's been argued that living in an open cluster could maybe lead to more hot Jupiters. It's also been argued that living in an open cluster can lead to fewer hot Jupiters. Certainly, the thick disk, there have been claims about very recent planet detections around stars in the thick disk, which is typically lower metallicity than the thin disk. So maybe the occurrence or types of planets might be different. Planets in the bulge, which we're learning about from micro-lensing surveys, it definitely seems like there are some differences there, although of course it's difficult to say because the micro-lensing biases are so much different from our other biases, but that's definitely an active area of investigation. The fact that a planetary system can be alone or can have other planets in the system, this is also something that has been very fruitful. So it's been claimed that maybe giant planets are less likely to have companions than lower mass planets. And maybe this tells us something about differing formation mechanisms for giant planets versus smaller planets. And then finally, system age. And so this is the thing which I am going to argue is both very, very powerful and perhaps the most powerful thing out of all of these, and also one that's very timely. It's very timely because we have lots of new data coming from satellites like TESS, from the Gaia satellite, and from large-scale ground-based surveys that give us ancillary information which help us figure things out that would otherwise be impossible to figure out. So I'm going to argue for the rest of my talk that system age is the parameter that we should be focusing on right now, both because it's timely and because it's very powerful constraints.
And it's a pun.
Okay, so the very first thing that I want to talk about is what's the time scale for planet formation and evolution? So the very first step is making the planets, and that happens when the parent protoplanetary disk is still around. So this is a classic diagram which quantified how long do protoplanetary disks exist by looking at the occurrence of disk signatures in young clusters as a function of age. So this is age in megayears on a linear scale on the x-axis, and the fraction of infrared excess, which is understood to be indicative of the occurrence of a disk on the y-axis. If one looks at young clusters, maybe 1 or 2 million years old, it seems like protoplanetary disks are ubiquitous. And as one moves to older clusters, the occurrence of protoplanetary disks goes down. And the typical understanding is maybe this is an exponential decay, and maybe the typical time scale is something like 3 million years. Although, of course, these all depend on pre-main sequence stellar evolution models to get an absolute age. And so there is some residual systematic uncertainty that maybe could push things a couple of megayears in either direction. Bottom line, planet formation happens, at least planets that have atmospheres, happens in the first 10 million years or so. And so what's going on in those first 10 million years? Well, planets are things that are built from the bottom up. So there's grains in the interstellar medium. They end up coupled with the gas into making a disk. They ultimately settle into the midplane. There's some growth there. Maybe there's some more growth in the midplane. Maybe they migrate. This is yet another thing that one could spend entire colloquia talking about. But there is some process which takes the millimeter-sized grains, the micron-sized grains that are in interstellar medium, and makes planetary embryos that are maybe something like the mass of the Earth, which have radii kind of like the radius of the Earth. So this is a process that goes on. There's a lot of unknowns yet to be solved in this, but it does happen because we have planetary systems. So somehow it all works itself out. So what happens then? After the disk goes away, lots of interesting dynamics happen, both secular dynamics integrated over many orbits and also very strong scattering events, which can happen very quickly. So these two diagrams, the first on the left has the number of years on a log scale from about 10,000 years to about 100 million years here. And these colors indicate that there is still a protoplanetary disk present at that range of separation. These black curves indicate the locations of giant. So these giant planets open up gaps in their parent protoplanetary disk. They stay more or less where they started out while that disk is still there. But once that disk goes away, a source of dissipation is removed from the system. So now these planetary systems start to exchange angular momentum. Eccentricities can be excited to the point that orbits can cross. And if orbits can cross, there can be strong scattering. And what happens here is this initially 3 giant planet system experiences an ejection, leaving behind only a single giant planet. And so this process is called planet-planet scattering. It's been hypothesized to explain eccentricity distributions, inclination distributions, lots of different observables. And if it happens in the strong scattering limit, it happens very quickly, maybe 10 to 100 million years after the formation of the system. One can also have a similar process here. I illustrate over here, which something similar happens where there's this illustrates the eccentricity and inclination excitation, where these planetary systems presumably start out on very circular orbits with low inclinations aligned with the disk. The disk is very effectively damping it. But when that disk goes away, you can have these strong scatterings, and one can end up with significantly higher eccentricities. We have absolutely nothing like this in the solar system, but that's not an atypical eccentricity for a giant planet, and a significant inclination between the planet's initial orbit and the orbit it ends up on. So if we could, oh, I'm sorry, Adrian.
I was just wondering, why is it such a sharp cutoff
in the disk?
The outer part of the disk at the top there. Microphone. Oh, actually, I think the ceiling mics are on.
No, the ceiling mics are not on. You do have to use them.
Oh, okay. I was asking why there's such a sharp cutoff in the existence of the outer parts of the protoplanetary.
Like right here?
Yeah, that was just to the right.
That's
sorry,
oh,
edge to the right.
Oh, here. That's just so it's thought that the nature of disk dissipation happens very quickly, and so this isn't done self-consistently in this model. This is imposed, but it is thought that it happens quickly. Okay, so also in that 10 to 100 million year range of time scale, the atmospheres of planets can change. So we think that a planet that makes it, or that forms during the era when its parent protoplanetary disk is around, will accrete an envelope. If it accretes a big envelope, then it's very robust to what happens next. But if only accretes a tenuous envelope, and in fact, this is what we think happens for most of the planetary systems. As I said, most planetary systems are low mass, most planetary systems are small. Most of them probably only accrete a small envelope of hydrogen and helium. Excuse me. The insulation that that planet experiences from its host star can cause that envelope to escape. And so this diagram has 3 different models for the amount of mass that's lost in a given time interval for a planet that's a ball of rock with some hydrogen and helium on top. And the amount of mass loss peaks in the range between a million years in the system's age. And this phenomenon is thought to have been seen very strongly by Kepler, producing the so-called Fulton gap. And so the physics of this process is not yet fully understood, but if one wants to explore it while it's happening, one needs to be able to find planetary systems in this range of age, and then also have reasonable constraints on the ages of the stars to watch this process happen in real time. Tidal evolution, which will be a recurring theme throughout this talk, is also something that can happen on now 100 million year to 1 gig year timescale. So now there are 3 things that tides can do typically. The first is illustrated here, is that tides can synchronize the rotation of a planet with its orbital period. And this is the thing that happens first. So this is semi-major axis in AU, on the x-axis eccentricity, on the y-axis. These different curves, the number next to it corresponds to the number of billions of years that a planet on this side of that curve would have its rotation synchronized with its orbital period. And so a typical eccentricity for a giant planet system is maybe 0.2 or 0.3. And so in the first 100 million years or so, the state where the rotation is synchronized to the orbital period will happen out to maybe 0.2 AU, which is pretty much the region of space we've explored with the transit technique, which tells us about most of the planetary systems that we're aware of. So certainly most of the systems that we have radius measurements, and I guess even an absolute number of systems we have, they are all tidally locked in this way. And if one could look at younger systems, one might be able to see this process happening, perhaps see the differences in the atmospheric circulation in detailed atmospheric modeling. So the next thing that tides do is they circularize orbits. So now this says in the next, say, 100 million to 1 gig years, the tidal dissipation inside the planet itself, the star raises a bulge on the planet, the bulge torques as the planet orbits because its rotation is synchronized with its orbital period. That dissipates orbital energy and angular momentum. Again, if one looks at a typical eccentricity, the numbers here mean the same thing. So if one looks at something like a gigayear with a typical starting eccentricity, then all of the planets with semi-major axes inside of about 0.1 AU will be circularized. And in fact, we see very strong evidence for this effect when we compare the close-in giant planets that we're aware of to more distant giant planets. It's very clear that this process of tidal evolution is happening. And if we were to look at young systems, we might actually see it happening in real time. Finally, the last thing that tidal evolution can do is tidal evolution can actually take enough energy and angular momentum from a planet's orbit to bring it close enough to its host star that it would be inside its own Roche radius and the planet will be tidally disrupted. So this diagram shows that imagine there's a planetary system at 0.05 AU, and if I were to run its tidal evolution backwards in time, how far could it have moved in as a function of time? And these different parameters, Q star, these basically say how much energy is lost on each orbital cycle. And it's the reciprocal of that number. So the smaller the number, the more energy is lost per cycle. That is, the more dissipative the star is. So this is extremely dissipative. And in that case, one can actually move a planet by something like 60 or 70% in a few gig-year main sequence lifetime. Perhaps these ones down here are a better approximation to reality, and that it says maybe the planet moves by 10 or 15% due to tidal evolution. So this process, until Jacob entered the scene, had not been observationally constrained. This was hypothesized, and as you can see, it depends a lot on this parameter, and this parameter is something that is completely impossible to constrain from first principles. So despite the fact that the physics in this situation is 19th century physics, it is not yet solved sufficiently to make accurate first principles predictions for these quantities. It's something that observations lead. And then as I indicated, there's this idea that the low mass, small radius planets we see maybe are balls of rock, and then they have some envelopes. Those envelopes could be hydrogen, helium. That's what I think, and I think that's what most people think now. But they could also be balls of water. And if all we have are mass and radius measurements, it can be hard to tell those things apart. So what I've illustrated here, this is a diagram which has age on a linear scale on the x-axis and the radius of a planet with several different compositions. So this planet up here is a 17 Earth mass thing with a significant hydrogen-helium envelope. This is kind of what Uranus and Neptune are like. Down here is a ball of rock, just 5 Earth masses. It's flat. This thing that has a hydrogen-helium envelope, the envelope cools with time and the envelope contracts because for a low mean molecular weight atmosphere, temperature is very important in the scale height. So as the temperature goes down, the scale height goes down. So for low mean molecular weight atmospheres, that's true. But for, say, a high mean molecular weight atmosphere that was made of water, it stays more or less the same. So again, if all I have is the radius measurement here, it can be very difficult to tell apart this ball of rock with some hydrogen helium on top and these essentially water worlds. And so this is something that measurements that looked at the radius distribution of planets as a function of age might give us some leverage on their atmospheric composition. Even with the James Webb Space Telescope, making these inferences, these differentiations between balls of water and balls of rock with hydrogen helium can be quite challenging because of things like clouds and aerosols in the atmospheres that consistently get in the way. And then finally, of course, there's go ahead.
When you say 100% H2O composition, you're talking about 100% of the atmosphere? It's still a ball of rock? Are you talking about like a water droplet?
It's a water world. It's like it's ice in the interior and perhaps an ocean on top.
Wow. Okay.
And so, of course, then there's also post-main sequence evolution. And so this looks very similar to the plot that I showed you for the dissipation of the parent protoplanetary disk, because in some sense, a change is happening on a time scale which is short. That is, the host star can lose half of its mass on a relatively short time scale, and the orbits of the planetary systems will expand. Their region where they gravitationally dominate grows, and now you can start to have overlap between the regions that the planets gravitationally overlap, whereas before they were sufficiently spaced. And so you can see something similar. Now this is time on a log scale. This grayed out area is the main sequence. These planets are happy secularly exchanging their energy and angular momentum. And then at some point, the host star's main sequence life ends, the system's planet's orbits expand, and that expansion causes a system that previously was stable to become unstable, and you can have these ejections again. So if we could have self-consistent ages across the main sequence to white dwarf evolutionary state, we might be able to actually even see some of these processes going on. That is the destruction of planetary systems at the end of the main sequence lifetime. Okay, so that at a high level is all of the wonderful things we could do if we had excellent ages from 1 to 10 megayears all the way up to 10 gigayears. Now, a lot of what I talked about is for very young systems, and of course, this is a very active area of research. There's a lot of excellent work. Trevor David here at the CCA has been a leader in the discovery and characterization of young planetary systems and going after many of these quantities. And it's important to say that we now know of a small number of very young and a growing number of maybe intermediate youngish age planetary systems that have been found with direct imaging and with the transit technique. And what these things have told us is that short period planets are in place by about 10 million years. And so there are some models for how giant planets close to their host star get in place that would say maybe you have to wait a little bit. And we're now consistently seeing that there are short period planets there pretty much as soon as we have any hope of seeing them. It's also now been shown from direct imaging observations there are also giant planets at tens of AU, which are in place even before the parent protoplanetary disk goes away. So planet formation at those distances is fast, and any seriously considered model has to be able to explain the existence of planetary systems both very close in and very far away in just a few million years. Now, ultimately, it's still true at this current point in time, the samples of small planets are small. I'm sorry, the samples of young planets are small, and so it's difficult to actually see these evolutionary effects if you only have a few points at any given age with relatively imprecise ages. We haven't yet seen direct observational evidence for a lot of the theoretical ideas I presented, at least for the young things. And so where one can actually make some serious progress is by looking at the planetary systems that are something like 1 gigayear to 10 gigayears old around main sequence stars, because that's where most of our planetary systems are. There are literally thousands of planetary systems spanning around stars spanning this entire range and age. And if one could do a better job with ages for mature planet host stars, one could make a lot of progress on both the tidal evolution stuff, which I talked about, which will be my focus, but then also going forward, also this atmospheric evolution, which has attracted a lot of attention in the field. Okay, so how is it one can actually get age inferences for solar type stars that happen to host planets? So one very excellent way to do this is to use age activity relations. So ultimately, we know that stars spin down as they get older, and the fact that that star spins down has a lot of very important effects on the structure of its magnetic field, obviously on its rotation, on its lithium abundance. It does a lot of things which we can measure. And the first one is the fact that the amount of activity that we see in a star seems to go down with time. So what this diagram shows is the 3 lines in the near-infrared calcium triplet. These lines are very, very strong. They're resonance lines. And so typically in a young star where there's a resonance line that has a very active corona, there will potentially be emission in the core of that line. And the amount of emission in the core of the line goes down with time as the star spins down and its magnetic field gets weaker. So there's less heating of the corona. And so these diagrams basically illustrate that for this near-infrared calcium triplet, a mature star will maybe look like that, and then going up like that is to younger and younger ages. And so if we have a moderate to high resolution spectrum, one can measure the amount of emission in the cores of these strong lines, and maybe if you've calibrated that, you can use that to tell you how old the system is. And so this is nice because once you've calibrated it, actually making the emission line measurement is model independent. You can always say more emission qualitatively means young, which is good. It works for individual systems, so you can go out to a single system that you care about, point your telescope, collect this data, and know for that single system what's going on. Some weaknesses of this technique, though, is that one needs high signal-to-noise data. Like if you have a high-resolution spectrum and you're looking for very small changes in the amount of emission, you need really high-quality data for single systems, and that can be expensive to obtain. This technique really only works for low-mass stars younger than the sun, so if one wants to look at more massive stars or stars older than the sun, this isn't really going to be helpful. And it's also, in the planet context, it's affected by the presence of a planetary system. So it has been shown that stars that have close-in planets have different emission properties than stars which don't. And so if one hopes to study planet hosts using a calibration which has been benchmarked with non-planet hosts, one could have biased results. Another very popular technique, which Ruth Angus at AMNH, also a member of the CCA community, is a leader in, is gyrochronology. So I mentioned again, the root cause of this chromospheric age-activity relation is that the star is slowing down with time. We can now measure that more directly. This diagram has log age in gigayears on the x-axis, the log rotation period of the star on the y-axis. This dot right here is the sun. And as stars age, they slow down until they get to the age of the sun, at which point it's less clear exactly what's going on. And so this technique works. Again, it's model independent. Qualitatively, you can always say the slower rotating thing is likely to be older. You need to use a model if you want to calibrate it and actually get a certain number of gigayears for a certain rotation period. Again, this is nice. It works for individual systems. If you have a TESS light curve, if you have a Kepler light curve, you can infer this quantity and then say something about how old the system is. The weakness is that you need that precise space-based photometric data, and we don't have that with a long enough duration, with enough sensitivity for every star we'd like to do this for. And so currently, this is limited to the Kepler, K2, and the TESS continuous viewing zone fields. As more data, as more large-scale photometric data becomes available, thanks to TESS, thanks to Plato in the future, maybe we'll be able to do this more elsewhere, but right now we can only do it in these fields. It really, so right now, only works for solar-type stars younger than the sun. If you want to go to stars that are earlier type than the sun, it's not going to work so well. And if you want to go to stars that are older than the sun, you face the duration limit, which we have from our photometric surveys, and also the amplitude of the signal gets weaker. And then again, this signal is possibly affected by the presence of planets. So I was just arguing that tidal effects can transfer angular momentum from the planet's orbit into the rotation of the host star. If you do that and you're trying to use the rotation of the host star to figure out its age, if you have a calibration that was based on non-planet host stars, and then you look at it, planet host stars, there can be a bias. A technique which has gotten an enormous amount of attention since the launch of the Kepler Space Telescope is asteroseismology. So this is extremely powerful. This is another observational diagnostic of stellar structure. And unlike most of the things we can observe, it doesn't just tell us about the photosphere of the star, it tells us about the interior. And so this diagram illustrates what's possible for a very close, very bright solar-type star. So this x-axis is the difference in age for two stars in a wide binary, which presumably have the same age, normalized to the sum of the squares of the uncertainties in the individual age estimates. These different points are from different asteroseismic models. These are the two Kick numbers for these stars right here. And so the age of this binary system is maybe something like 7 gigayears. And the dispersion from between these two stars and all of these different models is something like half of a gigayear. So this asteroseismology, in the most favorable circumstances, can deliver age precision better than 10%. So this, for the stars where this works well for, where one has the best data, this is the best thing that you can do. It's good because it has a solid physical basis. We actually think we understand how the stellar oscillations work in the internal structure of the star. As far as we can tell, this is unaffected by the presence of planets. Certainly it's affected by binary stars, but maybe at the planet level it's unaffected. And again, it works for individual systems. If you have a single star and you have all the right data, you can execute this measurement and get a very good age constraint. The problem now is it's model dependent. You have to use a stellar model to interpret these observables. And so if your stellar model has a problem, your inference will also have a problem. And we think our stellar models are very good, but maybe they're not good enough to deliver the 10% precision that seems to be indicated by this analysis. This is another technique that needs long duration, high cadence precision photometry. So again, you can only do this in the Kepler K2 or TESS continuous viewing zone. That's not the whole sky. It's not every star we'd like to do this for. And because the amplitude of the signal that we see for solar-type stars scales with luminosity, it only works for stars maybe a little bit brighter than the sun. If you want to do this for a late G or K dwarf in the light curve, you're going to have a difficult time. So a technique that has been around for a very, very long time is the fitting of isochrones to observational data. This is an illustrative example where maybe we have some broadband photometry and an absolute magnitude for a star. We have some theoretical stellar models, and we say what theoretical stellar models can produce the observables that we observe for the star. This is another very, very powerful technique because it has solid physical basis. We think we understand stellar evolution reasonably well for solar composition, solar type stars. It's unaffected by the presence of planets. It works for individual systems. That's all good. And now, thanks to Gaia, we can do this analysis for hundreds of millions of stars, whereas in the era of Hipparcos, before we had Gaia, we could do this for tens of thousands of stars. So the precise astrometry from Gaia gives us distances. We turn those into absolute magnitudes, has caused an enormous advance in the utility of this technique. Once again, though, this is model dependent. If you want to use the grid of isochrones to fit to your observables, you need to rely on the fidelity of the grid of isochrones. For main sequence stars, they pretty much sit there and don't do anything for most of their main sequence lifetime, so the change in the observables with age is very weak. Even with Gaia, it can be difficult to get precisions better than about 25% for a main sequence star. And then, of course, these are limited by the usually significant uncertainties in things like stellar effective temperature and composition. So if you don't have the star characterized in the best possible way, your fit to those observables will also be degraded. And so all of these things that I've talked about to this point are either widely applicable but model dependent, or narrowly tailored but perhaps have a model independent property that's qualitative. What would be ideal would be to have something that is broadly applicable and also model independent. And so this is a technique which is certainly well known in galactic astronomy, but something that I pioneered in the context of exoplanet host star ages while I was a postdoc. And so the idea is a thin disk stellar population is formed from cold gas in the midplane of the Milky Way. One turns that gas into star particles, and once those star particles have been created, they start to live their lives in the galaxy. They interact with tidal arms, with other transient features in the disk, maybe with molecular clouds, and each individual star starts to experience random kicks from each of these interactions. And so that population, which initially started on nice circular orbits, going around the galaxy almost exactly in the midplane of the Milky Way, starts to expand in phase space. So its scale height distribution starts to change, and it's the velocity dispersion of the particles starts to change. And this is monotonic. It grows with time. And in particular, it grows eventually to saturation, but the point where it comes to saturation is about the age of the Milky Way's thin disk, and it turns out almost all of the planet host stars we know about are in the Milky Way's thin disk. So this is quite powerful to study ensembles of objects in the solar neighborhood that host planetary systems. So this is nice because now it's model independent. This just happens. This is a property of stellar populations in the galaxy, and it works over all age ranges. It'll work between 10 and 100 million years, and will also work between 5 and 10 gigayears. It's unaffected by the presence of planets. The planets are a tiny, tiny change to what this star particle is doing as it lives its life in the galaxy. And again, this is the sort of thing that Gaia data has made applicable on a much larger scale in a much more powerful way than we would have been able to do before Gaia. So the weaknesses of this technique now is it only works for ensembles of stars. If you were to give me a single star and I were to calculate how it's moving through space, maybe it would give me a hint of what it was, but it certainly wouldn't be deterministic. For the time being, this is only relative ages, that I can only say this population is older than that population, but I can't say how many gigayears older the populations are different. Well, that's definitely something we're working on. And this is disk star and location specific. So the galactic dynamics people in this audience will, of course, ask me why I haven't used actions instead of velocity dispersion. And if I were going to do that, I would have to specify a model for the galactic potential. It would make it model dependent. And that's not supposed to be a big deal in terms of that we think that the galactic potential near the sun is pretty well constrained. But what I'm going to do, I'm only going to do in a location specific context. I'm only looking in the solar neighborhood. I'm not trying to self-consistently compare stars that are 5 kiloparsecs from the galactic center with stars that are 13 kiloparsecs from the galactic center, where things like actions are objectively necessary. So now I'm going to focus on hot Jupiters for this first science result based upon this galactic velocity dispersion technique. And so this is the first class planetary systems discovered around sun-like stars. 51 Peg B, you might have heard, first planet around a sun-like star that was discovered was an example of this class of object. And they're defined roughly by their presence in this blue box between something like 10 Jupiter masses and something like 0.1 Jupiter masses with an orbital period less than about 10 days. And so because of the biases of the transit technique, we have hundreds of these objects, and they're easy to study because we have so many of them. So now if I look at what the of this population of planets is, now it's mostly these things inside of 10 days, you can see that the eccentricity distribution of these longer period things extends to larger values than the eccentricity distribution of these things that are much closer in. That is, this is observational evidence of that second tidal effect that I talked about in my introduction. That is, we unambiguously see the tidal dissipation has circularized the orbits of these close-in giant planets. And the obvious implication is this eccentricity damping that turns this initially eccentric orbit into a circular orbit. But as I mentioned, there's this prediction for tidal decay, which happens on an order of magnitude longer timescale. What evidence do we have for that? It turns out that timescale is given roughly by this equation, and ultimately the amount of time it takes for the planetary system to fall in is something like 2 gigayears times this parameter Q star prime, which encodes how much energy is lost in the star on each cycle, normalized to 10 to the 6, which is thought to be a reasonable point. But it could also easily be the case that this could be 10 to the 5, or this could be 10 to the 7. So it could easily be the case that this tidal dissipation timescale is less than a gigayear, or it could be 20 gigayears, that is longer than the main sequence lifetime of the star. And theoretical models are not in general able to predict what that parameter is. So one needs to go out and observationally test the question whether or not hot Jupiters are decaying on a timescale which is comparable to the main sequence lifetime of their host. And so the approach that we took was to compare the velocity dispersion of stars that we see hot Jupiters around with the velocity dispersion of stars which have similar Gaia colors and absolute magnitudes, but do not have hot Jupiters. And so you might ask, well, just because you don't see a hot Jupiter doesn't mean there isn't one there, but hot Jupiters are intrinsically uncommon. Only about 1% of stars like the sun in the solar neighborhood have such an object, and so if I see one, it certainly has one, and if I don't see one, there's a 99% chance it's not there. So there certainly will be some residual contamination in our comparison sample, but it's probably negligible. And so this diagram here illustrates the locations of hot Jupiter hosts in this Gaia color magnitude diagram. So what we do is for each object, we randomly sample some other stars in the same volume of space in the de-reddened Gaia color and absolute magnitude. We do that for each system. We calculate the velocity dispersion of the two populations. We compare them and save the result. And then we do this many, many times to fully sample from the solar neighborhood velocity dispersion population. And the result is this diagram. So this is the U, V, and W plane, which are the three ways that velocities in the Milky Way are typically parametrized. The blue ellipses in the background are the velocity dispersion of the matched control sample. The individual points are the velocities of the planets themselves, planet host stars themselves, and the blue ellipses are the velocity dispersion of the giant planet host sample. And so this is the 1 sigma, 2 sigma, 3 sigma contours. So this is for F stars and G stars. What you can consistently see is that the velocity dispersion of the giant planet host sample is smaller than the velocity dispersion of a matched sample of stars that do not host giant planets or short period giant planets. And so one can roll up all of this stuff into a single histogram, and this is the result. So this blue curve is a histogram that shows the velocity dispersions from individual random samplings of the solar neighborhood population matched to the hot Jupiter host star population. And this orange line is the velocity dispersion of the hot Jupiter host sample themselves. So clearly, this velocity dispersion is incredibly inconsistent with random sampling from this matched control samples of velocity dispersion. That is, the hot Jupiters have a colder velocity dispersion and therefore have a younger age. That is, hot Jupiters are a transient population. They only exist around relatively young stars. Now, these are not stars that are 100 million years old, but they are stars that are closer to the beginning of their main sequence evolution than a randomly selected star of similar properties in the solar neighborhood. Now, you see this diagram and you might think, well, we know that giant planets are more commonly found around metal-rich stars. Maybe there's an age-metallicity relation in the thin disk. Maybe that's why you see this phenomenon. It doesn't have anything to do with tidal evolution. So now we can execute the same experiment now on stars which host giant planets that have orbital periods in excess of 10 days. That is, things where tidal evolution in this way shouldn't do anything to them. But the giant planet host star metallicity correlation is still approximately the same strength. And so what you can see here now is that the orange line that corresponds to the longer period giant planet hosts is fully consistent with random sampling from the field population. That is, there's no reason to believe that the result I showed you on the previous slide has anything to do with an age-metallicity relation. It really is related to the fact that there is a giant planet with an orbital period less than 10 days around that star. And so what we argue is that this phenomenon, or this observation, is best explained by us actually seeing these hot Jupiters disappearing. That is, this is the first indirect evidence that hot Jupiters are destroyed by tidal evolution while they're host stars on the main sequence. So we can go back to 1995, and it was known right after the discovery of 51 Peg-b that hot Jupiter systems were formally unstable to tidal evolution. That is, there was not enough angular momentum in the systems to reach the state where the rotation, the orbit of the hot Jupiter was synchronized with the rotation of the host star. But whether or not the tidal dissipation was efficient enough for this to matter, or if it would just stay in this unstable state for an indefinite time, was unknown until Jacob's analysis. And so because we see the hot Jupiters being destroyed, we can set upper limits to Q. That is, we can say Q must be more dissipative than the value we see to explain the disappearance of hot Jupiters before the main sequence lifetimes of these stars end. And because this is a statistical measurement, it mostly applies where we see planetary systems. That is somewhere between 2, or we see most of the hot Jupiters are discovered by ground-based transit surveys, and because of the selection effects, that puts them between 2 and 6 day orbital periods. We can say that maybe the typical Q in the star is something like 10 to the 6.5. So remember that number. So shortly after Jacob and I published this result, there was direct observational evidence for the first time for this happening in a single system. And so this was for the Wasp-12 system. So Wasp-12 is special because it's a massive giant planet with an orbital period less than 1 day. And so it was thought to be one of the most likely systems to actually be seeing its orbital period slowly shrinking with time. And so this top diagram shows what people were seeing. That is, they were seeing the transit times change. The problem with this is when one only looks at the transits, it's possible that one could also be seeing apsidal precession of a mildly eccentric orbit. That is, the reason the individual transits start getting closer together is not because the orbit is shrinking, it's just because the pericenter is moving along our line of sight. So this paper had the result where it not only had the transits, it used Spitzer to look at the occultations, that is actually seeing the hot base side of the planet go behind the star and seeing the dip in the brightness of the star in Spitzer. And once you have both of those data, you can easily disentangle the point where if it was precession, then the transits would be getting closer and the occultations would be getting further apart, whereas they would both be getting closer together if the orbit was shrinking. And that is indeed what they saw. So not only did we see indirect evidence for this at the population scale, very shortly after our result was shown direct observational evidence for a single system. And in particular, the Q constraint that was derived from those data is consistent with what we said. That is that the value of the tidal dissipation inside the star had to be below that level. Okay, so that is the answer to the second oldest question in exoplanet astronomy. So the first was, how did hot Jupiters get there? That's still something we're grappling with. But the next question is, what happens to them after they get there? And now we know the answer. The answer is that they're destroyed by tides. Another question that one can explore using this same technique is, what's the fate of ultra short period planets? So this is a class of planetary systems that was first characterized by the Kepler Space Telescope. These are rocky planets that have planetary masses less than maybe about 10 Earth masses and have orbital periods less than 1 day. So if you can think of the most hellish world that you could conceivably actually put your feet in the lava on, it's this kind of object. And in fact, these are things that are in this blue box right here. They're an intrinsically rare class of planets, but again, thanks to the biases of the transit technique, we know of lots of them. And I actually have a long history with this class of object. I wrote a paper in 2010 when only one of these objects was known, and I specifically said Kepler is going to find lots of planets like this, and in particular the formation mechanism is going to be systems of multiple planets that have secular exchanges of eccentricity that's going to drive an inner planet close to the host star, at which point tidal dissipation inside the planet is going to circularize the orbit, and it's going to leave behind an ultra short period planet. So if that's true, and one takes, or even if that's not true, just these things exist, and one takes the scaling relation I had shown before and says, we saw hot Jupiters being destroyed by tides. If the efficiency of dissipation is independent of the forcing amplitude or the period, that is a constant Q model, which is what most people would use, then the fact that we see hot Jupiters being destroyed implies that the time scale for USP destruction is something like 1/10 of the time scale for hot Jupiter destruction. So if everything is the same, if there are no changes, then we should see ultra short period planets as a transient population as well. And in particular, this can also be used to separate these two different USP planet formation paradigms. There's the paradigm I outlined that I predicted has been elaborated and by much more careful analyses than what I had put forward in 2010. And there's also an idea that's been put forward that it's not the tidal dissipation inside the planet that's causing it to lose orbital energy and angular momentum. It's the tidal dissipation the planet is doing inside its host star that's causing its orbit to shrink. And as I just argued, if the tidal dissipation in a constant Q model is correct, then that is completely a plausible explanation. And so Jacob and I did the same thing. We went to now the Kepler field, where most of the ultra short period planets that are known reside. We did the same thing now, not in the solar neighborhood, but in the Kepler field, where we selected stars that don't have ultra short period planets, that have similar de-reddened Gaia colors and absolute magnitudes. We can say the same thing as before, that is ultra short period planets are rare. That is, so if we don't see one, that means there's probably not one there. So it actually is a reasonable differential measurement. And we can calculate the velocity dispersion of the ultra short period planet host population, compare it to the field, and evaluate whether or not ultra short period planets are a transient population. Are they falling to the same fate as hot Jupiters? And what we found is that they have a velocity dispersion that's indistinguishable from the field. That is, there's no reason to believe that ultra short period planets are a transient population. That is, they are not experiencing the same fate as hot Jupiters. That is, a constant Q model is not a good explanation for tidal dissipation in the exoplanet regime. And so that rules out this entire class of ultra short period planet formation models, which specifically say, let's deliver a planet close to the edge of its parent protoplanetary disk while the parent protoplanetary disk is still there. And then let's use tidal dissipation to inside the star to slowly move it in. We can do the same thing as before now, because we don't see decay, we're setting lower limits on the amount of dissipation. And in fact, our estimates for the lower limit are inconsistent with this measurement for Wasp-12. Wasp-12 is a massive giant planet in the same range of orbital period. So we're seeing very, very strong evidence that this Q star parameter, the amount of dissipation inside a host star for every orbital cycle, depends on the properties of the forcing. This is something that was theoretically anticipated by Gordon Ogilvie and Adrian Barker, but it wasn't something that there was any observational evidence for until we executed this measurement. So we are seeing that tidal evolution is more complicated than was thought in these simplistic. Okay, so I have, Jacob and I are working on several other things related to using this same technique to study tidal evolution in short period planetary systems. I don't have time to go into them. Jacobs hasn't submitted those papers yet, but I'm happy to tell you about our preliminary results for those things offline at the reception afterwards. So what's the future of stellar ages? So this is actually, I'm sure you hear this all the time, where this is the golden age of astrophysics in many ways, but it is also the golden age of astrophysics when it comes to stellar ages. And the reason is because there's a lot of effort right now in building better stellar evolution models because of the data that Gaia has provided. Gaia has told us an enormous amount of stars. It's about stars. It's given us lots of benchmarks that we can then use, or stellar evolution modelers can use, to tune the parameters in stellar evolution models for solar type stars to give us the best age inferences from observables. We also have all this complementary data. We have these rotation periods. We can use that to further develop gyrochronology. We'll have a lot more asteroseismology data for stars like this thanks to Plato, the European Space Agency's upcoming transit survey. And all of these things together are going to make isochrone analyses, which we can apply pretty much anywhere in the sky thanks to Gaia, much more powerful. So this has historically been one of the most difficult inferences in exoplanet astronomy, that is to infer the age of an isolated solar type star. But my prediction is that over the next 10 years, this is going to be much, much easier than it's been in the past. And we are actually going to be able to have reasonable age constraints for the isolated stars. And this is going to be enormously important, not just for planet formation and evolution, but also for numerous fields of galactic astronomy. Another reason this is going to change is that there are large-scale surveys, both photometric and spectroscopic, that are giving us even better observables. So things like the composition of the star, the effective temperature of the star from spectroscopy, radial velocities, which are a necessary component to the velocity dispersion analysis I described. All of these big ground-based surveys are going to be giving us more and more data. So not only are we going to win because of the space-based stuff and improved stellar modeling, we're also going to win because of all the ground-based data that's becoming available. So I'm very optimistic about the future of stellar ages. Things are going to be much, much better than they have been in the past, and there's going to be a lot of very, very interesting astrophysics going on in this subfield going forward. So my conclusions, first of all, the age inference problem for isolated field stars has been difficult, but it is getting much, much easier than it's been in the past. Problems will remain, though, for exoplanet host stars because of this exchange of angular momentum, because of the interactions of the magnetic fields of the star and the planet. One can overcome a lot of those issues for planet populations by using the galactic kinematics of these planet host stars in comparison to stars that don't host that class of planetary system. And in particular, I showed that the velocity dispersion technique requires that hot Jupiters around solar type stars are a transient population. Only relatively young stars have a hot Jupiter, relatively older stars generally don't. And finally, that this class of ultra short period planets, that is rocky planets with orbital periods less than about a day, even though a constant Q model should suggest that those things should also be destroyed, they're robust. They are not a transient population. They live for the entire main sequence lifetime of their host star, and their long-term existence tells us that the amount of tidal dissipation inside of a star is a function of how that star is being forced. And it also allows us to say that the best explanation for the existence of ultra-short period planets is that they're in multiple planet systems, that the innermost planet has been driven by secular interactions to high eccentricity, and then tidal dissipation inside the planet has damped that eccentricity, and left behind an ultra-short period planet. Great, that's all I have to say. I'm very happy to take questions.
Questions in the room or
So there's
via chat?
There's two.
Thanks for that talk, Kevin. That was really interesting. I was especially excited about this evidence of the transient nature of the population of hot Jupiters. I was wondering about kind of the fate of these systems after the hot Jupiter gets ingested, because I think that makes a couple of predictions. One being that the star will show evidence of this and say like enhanced lithium abundance, spin up. The other is that the planetary system will be disrupted. You would probably have no short period planets left because of the Jupiter sweeping in. So I was wondering whether there's an experiment to be done there by looking for these systems that have those two markers.
Yeah, so the two things one could look for is one could look for the angular momentum which has been deposited. So for example, we know that hot Jupiters are more common around metal-rich stars. So maybe you would expect to see that there is some fast rotation phenomenon that seems to be more common around metal-rich stars, perhaps something similar for the lithium abundance that would also seem to be more common around metal-rich stars. The problem I foresee, though, is that hot Jupiters are intrinsically rare. Even for a metal-rich star, this is maybe a 5% sort of thing. And so I think one would need very precise estimates for a large number of stars over a range of metallicity, perhaps to tease something out. But it is in principle something that's possible. So if this explanation is correct, then it should be the case that there should be some population of metal-rich stars that has high lithium and has fast rotation relative to what it should be. And that's perhaps something we can look for in the future going forward.
Let's do that.
And then the second question, so there are not so many close in, so we know from transit surveys that if you see a hot Jupiter, there's not often that many things on the inside of it. Now you might say, well, that's because they're inclined, and the hot Jupiter is especially effective at pumping the eccentricity and inclination of its companions, so maybe they are there. But it would be difficult to say, I think, much about that specific thing because of this problem in that even we don't really know how many are out there right now because of hot Jupiters being so effective at exciting eccentricities and inclinations. So I'm less optimistic about seeing that than I am about the maybe fast rotation and lithium abundance in metal-rich stars.
Let's do Rachel next, and then Matteo, and then Ruth.
Hey, Kevin. So I think this may be a much more naive version of Megan's question. And if that's the case, apologies for being a dumb galaxy person. But I'm trying to picture, are the hot Jupiters tidally destroyed like long before they would affect the host star? Or, I know there's evidence that sometimes the star can actually kind of eat the planet. And I think that's what you were talking about in response to Megan's question. So do you have a sense for which of those scenarios is most common?
Well, so I think what happens is that, so it depends on the internal structure of the planet. Certainly it will lose its hydrogen-helium envelope first, but by the time it gets so close to that, the ball of rock that remains, I think, will also probably be close enough such that the ball of rock in most cases will also probably be consumed. So we think that there's probably a 5 to 10 Earth mass ball of solid material at the bottoms of these giant planets that in addition to the envelope will also eventually make its way onto the star. But I admit I haven't done a detailed calculation about this.
She's frozen. She looks so confused.
Well, that was super interesting, Duncan. Just a question, and maybe I missed it, maybe you said that. A lot of your results rely on this measurement of the velocity dispersion, and velocity dispersion can depend on things like binarity. So I wonder if you look at that, because there could be a bit of bias. For example, if hot Jupiters are not found around stars in binary system, that will maybe reflect in your distribution.
Yeah, so that is a good point. So the type of binaries that can affect the velocity dispersion at the kilometer per second level are relatively short period binaries. I'm trying to find this slide right here.
Mm-hmm.
So if you want to affect the velocity dispersion by more than a kilometer per second, the binary has to have an orbital period that's less, I don't know, something like 50 days. And so if there were a binary star inside of 50 days, we probably wouldn't see the hot Jupiter. We think that those sorts of binary systems are inhospitable to making a hot Jupiter in the first place, and they would definitely not produce these things either. So I think that, and then the wider binaries, which are definitely right, could be there. They're not going to affect the velocity dispersion that we measure because the reflex velocity of a distant star is going to be less than a kilometer per second.
Isn't that it's going in the right direction? Like if you have at the population level.
But they wouldn't. These would be even less likely to be there if the star were there. So I don't think the presence of a binary companion is going to differentially affect things. But perhaps I have to think about this a little bit more deeply.
And going back to the question about what will happen to the hot Jupiter, the first thing will happen in that case for main sequence star is that it will feel its rush flow, and so the envelope will be accreted, and then probably what you said is correct. Core will impact and be destroyed at some point in the envelope. So there could be actually some signature. I've done some work on that, but it's interesting that you find that this might happen actually on the main sequence.
Yeah, so that's my prediction, is that it does happen on the main sequence, for at least for the. So I should say it happens on the main sequence for the type of hot Jupiters that we have the most of observationally. But there are more hot Jupiters at 8 to 10 days than there are between 2 and 3 days. And so in some sense, the most likely outcome for a hot Jupiter maybe is a little bit later. It's the ones that we see observationally are falling on the main sequence.
So I'm going to ask for Ruth is asking about, could age, Ruth Angus, who's also faculty at the Museum of Natural History, could age-related exoplanet detection biases affect the results, particularly regarding cold Jupiter and the ultra-short period exoplanets, which are more difficult to detect than the hot Jupiters?
Yeah, so that is an excellent question. And so you can see a hot Jupiter around a star that is maybe half a gigayear old, whereas these Doppler surveys may be focused on stars that were about 2 billion years old or older. But the amplitude of this effect, in some sense, has been decreasing with time as Doppler surveys have become more and more able to access relatively younger things. And so qualitatively, that's true that the bias does go in the right direction. But if one were to ask, based upon all the other things that we have for these hot Jupiter systems, that is, if one looks at qualitatively what's been presented at the discovery papers about the rotation period, the activity, all these other things, it doesn't seem like most of them have ages less than about a gigayear. It seems like they have qualitatively have the same age range. So it's not impossible that could be so, but it would be really, really weird in the sense that all the discovery papers fail to report all these other bits of data which are suggestive of youth.
So I have another question. Go ahead, Bill.
So this is maybe the fourth version of Megan's question. Sorry, but is it possible to convert the hot Jupiter result into an estimate of how frequently you should have these planets that are doing this special overflow? Because presumably that would have first of all, it would be super cool to find even one such thing, and it must have some.
Yeah, so I think yes, that is something one could do, when one could make a prediction about the rates of this sort of event, but we have not taken any steps towards doing that. Our hope is that perhaps, we don't have any concrete plans, but we're hoping once we've calibrated this using another type of analysis that we're interested in, then maybe we'd be able to make a more concrete thing per unit time. Right now, it's very qualitative, which makes it hard to make a numerical prediction.
Sorry, guys. Yeah, I think that's super interesting, and I would love to talk more with you about the existence of short period planets around evolved stars, because we know they exist, so where do they come from? But that's a long discussion. I think more like in the shorter term, I was just curious what you think is, for example, like the new metallicities that we're going to get from Gaia DR3. It would be really useful for sort of redoing your Q-star analysis for all of those obscular systems.
Yeah, so that would certainly be very helpful if one had metallicities for lots of stars that one could also do a kinematic analysis for. Then one could remove that potential caveat, that is that there's no reason for there to be an age metallicity relation, but maybe there's going to be something that is very subtle that had been missed until you have Gaia give us a million spectroscopic metallicities. So yes, I think that would be an excellent thing to do, is to potentially revisit this with the future Gaia data releases. It's also possible that the binarity question could be looked into more detail once Gaia has told us what the astrometric binaries are. So I think there is still going to be a lot of work to be done to both continue to verify this interpretation and also to expand the use of this technique in other planet formation evolution contexts.
I'm going to take it a different direction, which is that I share your optimism for it being a great time and there being a lot of potential in us getting better ways to estimate ages. I'm curious if you could put a mass range on your optimism.
So I was mostly thinking about stars like the sun.
Okay.
Because that is,
when you give this talk to other places, please emphasize that.
Okay. So that's what my expertise in.
Right.
For low mass stars, of course, they don't do very much on the main sequence. They mostly just sit there, and so that makes it difficult. That makes it difficult from a modeling perspective to constrain them. But for example, this technique could be applied to any collisionless particle. So you could apply it to brown dwarfs as easily as you could apply it to O stars.
Right, yeah, so I'm very optimistic about using the kinematic, so to use the better constraints on the kinematic relation that then we can apply to lower mass stars. Good, Adrian.
I think most of the galactic dynamicists here would not advocate for using actions, but I am going to advocate for using actions just because I'm curious. It does contain more information, and in a relative sense, we probably know the local potential well enough that it could give you more information about. Like, in some sense, here it would increase the precision with which you can make a claim that the Jupiter hosts are different from.
Yeah. So I do agree with you that in the intermediate to long term, that is the thing that should be done. But right now we are using this. We are trying to emphasize that this is model independent, and as of course you said, it
doesn't work with your brand or whatever.
The branding, and that is exactly there are other than this technique, there's probably a fraction, like there's really no other way to do anything in a model independent way for stellar ages, and that's really what we're trying to market. But I think on the medium to long term, I think you are correct that we should be transitioning to using actions and not just doing the velocity dispersion.